In the last episode, we proved that adding noise to an image is just a random walk into chaos. But if the noise is truly random, how does the AI know which way is back? The secret isn't a digital paintbrush. It's a time machine made of vector fields. Zoom out, and it isn't just one dot. Thousands of points, all wandering through the exact same invisible field, all pulled along their own paths, all arriving at their own recognizable shape. Somewhere behind this entire scene, quietly doing the work, sits a neural network we call a U-Net. By the end of this episode, you will understand exactly what it is calculating, one arrow at a time. Last episode, we did something that felt almost sacrilegious. We took a perfectly good photograph and destroyed it on purpose. Beat by beat, 1,000 tiny random nudges buried a face, a sunset, a cat under featureless static. We proved that forward diffusion is really nothing but physics. Entropy, the same force that cools your coffee and melts your ice, running forward exactly on schedule. That part is easy to believe because it happens by itself, with no help from us. Reversing it is the part that should be impossible. Here's the wall every student hits the first time they see this problem. You cannot undrop ink into water. Once those ink molecules have spread randomly through the glass, there is no future sequence of random molecular collisions that reliably gathers them back into a single drop. It isn't against the rules of physics. Technically, it's just so astronomically improbable that it will never happen in the lifetime of the universe. Diffusion runs downhill, into disorder, and it does not run back uphill by accident. And yet Stable Diffusion, Midjourney, and every modern image generator do exactly that, starting from pure static and ending on a coherent photograph, every single time you ask. Physicists have another way to put this that's worth sitting with. Entropy isn't a strict law-forbidding reversal, it's a statement about probability. Ludwig Boltzmann showed that a disordered state isn't fundamentally different from an ordered one at the level of physics. It's simply a state that can be reached by vastly more possible microscopic arrangements. There are astronomically more ways for ink molecules to end up scattered through a glass than clumped into a single drop. So a scattered arrangement is overwhelmingly what you find if you wait. Reversing that isn't physically forbidden. It's just betting against odds so large they might as well be impossible. And that reframing is exactly the crack the AI slips through. It was never trying to beat those odds. It's solving a much smaller, far more tractable problem. Given this specific noisy point, what does the surrounding probability landscape suggest is the most likely explanation? That's not thermodynamics running backward. That's statistical inference, and inference doesn't care which way entropy happens to point. The resolution to that contradiction is simpler than it looks. The AI isn't trying to exactly reverse the physical process. It isn't tracing one specific ink molecule back to its exact starting position. It only needs to find its way back to somewhere plausible. Any point that looks like a real image, not necessarily the one it started from. To do that, it needs something forward diffusion never required: a map. Not a map of one image-specific noise path, but a map of the entire landscape of images. A sense, at every noisy point in that space, of which direction leads back toward something real. Build that map once, and reversing diffusion stops being magic. It becomes navigation. That map is exactly what the rest of this video is about. Just like last episode, we're going to abandon pixels completely and think geometrically instead. Remember the trick: every possible image, every face, every landscape, every completely random blur is a single point in an enormous space. A million-pixel photograph collapses down to one dot. We flattened that impossible space into a simple two-dimensional plane so we could actually watch it move. Let's bring that plane back, because this time we are not asking where a dot travels. We are asking what the terrain around it actually looks like. Scatter every photograph in a training set onto this plane, and something striking happens. They do not spread out evenly. They clump tightly. Photographs of human faces cluster near each other, because faces share enormous structural similarity. Two eyes, a nose, roughly the same proportions, arranged roughly the same way. Landscapes cluster somewhere else entirely. Every category of real image occupies its own small, dense neighborhood, surrounded by vast stretches of the plane that no photograph a camera could ever produce would visit. Why should real images cluster at all, instead of scattering evenly the way noise does? Because a photograph isn't just any arrangement of pixel values. It has to obey the physics of light, the geometry of real objects, and the statistics of natural scenes. Two eyes are roughly symmetric. Skies are usually up. Shadows fall consistently. Every one of those constraints removes enormous swaths of possible pixel arrangements from ever counting as a real photo. Which is exactly why real images collapse into a comparatively tiny, low-dimensional pocket of an astronomically high-dimensional space. Researchers call this the manifold hypothesis. Real data doesn't fill its space uniformly. It lives on a thin, structured surface tucked inside that space, the same way a sheet of paper is a thin, two-dimensional surface, crumpled into three-dimensional space. Now let's draw that density, the way a cartographer draws elevation. Around each cluster, sketch contour lines, rings that mark equally likely to be a real image. Near the center of a cluster, the rings pack close together. A steep, narrow peak, extremely likely to represent something real. Move outward, and the rings space out fast. The probability drops off a cliff within a short distance. This is a probability landscape. In the most literal sense we can draw it, and real images are its mountains. And what about everywhere else? The vast majority of the plane, the region pure noise actually lands in after 1,000 steps of forward diffusion. It is almost perfectly flat, featureless, no peaks, no valleys, just a low, uniform plateau of probability. Because random static, by definition, does not prefer any particular pattern over any other. A noisy point at t equals 1,000 could be sitting almost anywhere on this enormous flat plane. And from where it is standing, it has no visible clue which direction the nearest mountain even is. It's worth pausing on just how lopsided this split really is. If real images occupy a manifold, effectively a razor-thin surface, then almost the entire surrounding volume of the space is, by definition, everything else. Pick a random point in a million-pixel space, completely uniformly, and the odds it happens to land on something resembling a real photograph are effectively zero. This is sometimes called the curse of dimensionality. The more dimensions a space has, the more its volume concentrates far away from any particular thin structure sitting inside it. That's precisely why isotropic noise, the destination of forward diffusion, is such a reliable, information-free starting point. It could be starting anywhere on those vast plains, and reverse diffusion still has to find its way home from there, with no shortcuts and no hints about where it began. So here is the geometric version of the entire reverse diffusion problem, stripped of every irrelevant detail. You are a lost point, standing somewhere on this flat, foggy plane. Somewhere out there, you don't know exactly where, is a mountain of real images. How do you find your way there? One small step at a time, using only information available right where you are standing. Answering that question honestly, with real mathematics instead of hand-waving, is what the rest of this video does. At every point on this landscape, there is a single best direction to step if you want to increase your odds of standing on a real image. The direction of steepest ascent up the probability mountain. In calculus, the direction of steepest ascent of any function has a name, the gradient. And the function we care about here is the probability landscape itself, p of x. So the object we need, at every single point in this space, is the gradient of that probability. There's one wrinkle. Raw probability values are punishing to work with numerically. Way out on the flat plains, the true probability of any given noisy point is an unbelievably tiny number, and computers hate multiplying together long chains of tiny numbers. The fix mathematicians reach for constantly is to take the logarithm first. Logarithms turn punishing multiplication into forgiving addition. And, crucially, taking the gradient of the log of a function points in exactly the same direction as the gradient of the function itself. Same compass heading, dramatically friendlier arithmetic underneath it. Put those two pieces together, and you get the single most important object in this entire episode. The score function, written the gradient with respect to x of log p of x. Say it in plain English and it loses none of its power. At this exact point, in which direction, and how strongly, does the probability of being a real image increase fastest? That's it. That is the whole idea, hiding behind the intimidating notation. It is a direction and a magnitude. In other words, at every point in space, it is a vector. And a vector field, defined at every point in space, always pointing toward higher density, that is not an abstract calculus object anymore. That is gravity. Literally, imagine every cluster of real images as a planet, and the score function as the gravitational field surrounding it. Stand anywhere in this space, even out on the flattest, emptiest plane, and the score function still gives you a direction. However faint, however uncertain, it points you toward the nearest mountain of real data, the same way a distant planet's gravity still tugs, faintly, on anything in the void around it. Here's a detail that makes the score function even more practical than it first appears: properly normalizing a probability distribution, making sure it sums to exactly 1 across every possible image, usually requires computing a horrifically expensive constant, often called the partition function, integrated across the entire space. Most of the time, nobody can actually compute it. But watch what happens when you take the gradient of a log probability. Log of a distribution times a normalizing constant splits, by the laws of logarithms, into log of the unnormalized part plus log of the constant. And the gradient of a constant, with respect to x, is exactly 0. It vanishes completely. That means the score function never needs the normalizing constant at all. You can work with a totally unnormalized density and still get the exact right direction. This one piece of algebra is why score-based methods sidestep one of the most notorious computational bottlenecks in all of probabilistic modeling. Watch what this looks like across the entire plane at once. At every point, we draw a small arrow. In the exact direction the score function points from that location. Near a cluster, the arrows are strong and converge sharply inward, like the field lines around a magnet. Out on the flat planes, the arrows are fainter. The pull is weaker, further from any real structure, but it is never exactly 0. Every single point in this space, no matter how lost it looks, has just been handed an escape route back toward reality. This is the aha moment this entire series has been building toward. Reversing diffusion does not require an AI to memorize what every possible image looks like, or to somehow invert 1,000 steps of randomness exactly, molecule by molecule. It only requires knowing, at any noisy point, which direction is more real. Follow that direction, take one small step, recompute the direction at your new position, and repeat. That process, noisy gradient ascent up a probability landscape, is called Langevin dynamics, and it is a startlingly simple loop for something that looks, from the outside, like pure sorcery. So where does the neural network actually fit into all of this? Here's the single most common misconception to clear up first. The UNet is not a filing cabinet of pictures. It does not have a face, a mountain, and a cat photo stored somewhere inside its weights, ready to be pasted in on request. If it worked that way, it could never generate anything it had not already seen. And modern image generators clearly can invent things that never existed. So if it is not storing images, what exactly is it storing? The UNet is trained to do exactly one job. Given a noisy image, and how much noise it has been told to expect at this time step, output an estimate of the score function at that exact point. In other words, it is not predicting the picture, it is predicting a direction. Feed it a noisy dot in our two-dimensional world, and it does not hand back a cleaner dot directly. It hands back a single arrow, this way toward reality, roughly this strongly. In practice, most real implementations train the network to predict the noise that was added rather than the score directly. But here is the beautiful part. Mathematically, those two targets carry the exact same information, just rescaled by a known constant. Once you know precisely what noise was added, you also know precisely which direction points back toward the clean image, because you know exactly what got layered on during the trip out. Predicting the noise and predicting the score are simply two names for the identical arrow. There's a subtlety hiding in that training setup. The amount of noise in the image changes completely depending on where you are in the 1,000-step chain. A dot at step 10 is barely disturbed. A dot at step 900 is almost pure static. A single fixed function can't sensibly point toward reality for both of those situations using the same rule. The right correction is completely different depending on how much has already been destroyed. So the UNet isn't just handed the noisy point, it's also handed the time step, t, as an explicit input, usually embedded numerically alongside the image itself. In effect, we're not training one network. We're training one network that behaves like 1,000 different specialists, each an expert at exactly one noise level, all sharing the same weights. And crucially, the network can be trained on the one thing it is never allowed to see at inference time: the correct answer. During training, we take a real image, add a known, precise amount of noise to it ourselves using the forward process from last episode, and hand only the noisy result to the network. Because we manufactured that noise ourselves, we already know the exact direction back to the clean image. So we can score the network's guess against ground truth and correct it millions of times over until its arrows get reliably accurate. Why the specific U-shape? Because predicting a direction at every single pixel requires understanding an image at multiple scales at once: broad shapes and overall layout on the way down, fine texture and sharp edges on the way back up, with skip connections stitching the two halves together so no detail gets lost in the narrow bottleneck. But don't get distracted chasing the architecture diagram. Structurally, all that matters for this episode is the contract at its two ends. Noisy image goes in, one vector field comes out. Now let's assemble every piece into the actual reverse diffusion algorithm, stated in full. Start at t equals 1,000, a point sampled from pure isotropic noise, exactly where forward diffusion left us at the end of last episode. Feed that point into the trained UNet. It returns a vector, its best estimate of the score, the direction back toward real data. Take one small step along that vector, add a carefully calibrated dash of fresh randomness back in, and land at a slightly less noisy point, t equals 999. Then do it again. Feed the new point back into that same network. Get a new arrow. Step. Repeat 999 more times, each step nudging the point further up the probability landscape, back toward the dense, structured mountains where real images live. Watch it happen across an entire cloud of points at once, each one guided independently by the exact same vector field, and something like a photograph gradually condenses out of what was, a moment ago, completely formless static. It's worth asking directly, why not just take one enormous leap straight from static to a finished image, using the score function once? Because the score function is only reliable locally. It describes the best direction right here, not a straight highway all the way to a cluster. Take one giant step, and you'll likely overshoot, landing somewhere the network has never been trained to evaluate accurately. 1,000 small, cautious steps, each one recomputing the direction fresh, let the point continuously correct its course. The same way you'd navigate fog by taking short steps and rechecking your bearings, rather than sprinting blindly in whatever direction looked right at the very start. And that is the complete machine, a physics-based destruction process reversed by a neural network that never memorized a single picture, only a vector field, one gradient at a time. We now know exactly how an AI finds an image hiding inside pure static. But notice what we conveniently avoided this entire episode. We never once told it which image to find. Every arrow you just watched only knew how to reach something real, not a cat on a skateboard. So what if we don't just want any image? How does a handful of words reach in and warp this entire vector field toward one specific answer? That's episode 3.